Hello everyone. For today's video lecture, we're going to be talking about efficiency in rigid body systems. So with all of this, we're talking about work, power, and energy transfer. So we want to discuss the concept of energy transfer in all of this. So energy can't be created or destroyed. That's the first law of thermodynamics, kind of conservation of energy. But many engineering devices convert energy from one form to another. So this is considered an energy transfer. So something like a solar panel is going to turn radiant energy into electrical energy. Something like an internal combustion engine is going to turn chemical energy into thermal energy, into mechanical energy. And then something like a transmission just transforms one mechanical energy into another mechanical energy, maybe changing the torque for an increase in speed or vice versa. In dynamics, we're mostly going to be focusing on the mechanical energies. Thermodynamics is more the space for other efficiency measures. But for something like a transmission, we can still talk about efficiency. So the efficiency of a device is the percentage of useful work, energy, power, etc. That makes it from the input to the output. So it can be measured by taking the output, energy, work, or power, and dividing it by the input, energy, work, or power. So whatever we start with, we want to measure the same thing at the end there. So with this, eta, that is the Greek letter eta, is what we use to denote efficiency. So energy out over energy in, or work out over work in, or power out over power in. All of those should be equivalent to one another, so we can kind of use them interchangeably. So by rearranging those previous equations, we can use the input along with a known efficiency to predict the output of a system. So efficiency times power in is equal to power out. Again, we can substitute in work and energy for those in power values. And in mechanical systems, kinematics will usually constrain the motion, meaning that losses will play out as a loss of force or moment rather than a loss of velocities. So with this, if you imagine something like a gear system, the teeth can't travel through one another, so kinematics-wise, they are locked into a specific ratio of velocities. But for something like a translational system, we have the force out is equal to efficiency, force times velocity in over velocity out. So that is power in over velocity out would give us the force we'd expect out of some translational system. Rotational, something like a transmission. The moment we would expect out is the efficiency times the power in, so m times omega would be your power, over the angular velocity out. All right, so with all of this, this is kind of a way to predict the output based on the efficiency of a system. And we also want to talk about problems with inefficiency. Since energy cannot be destroyed, the lost energy doesn't really go away. It's just converted to a non-useful form, usually something like heat. So if we've got something like a transmission, if 90% of the energy or the power is making it through as useful mechanical output, the other 10% is being turned into heat. So in some systems, this built-up heat can further decrease the efficiency, compounding the problem. So if you get a really warm system, or if something like transmission gets really warm, you might end up burning off the lubricants, and that's going to further decrease the efficiency and kind of cause breakdowns as well. So efficient systems, or efficient mechanical systems, generally generate less heat. And that less heat is usually a good thing because you don't have to worry about cooling the system as well, or the issues that might be associated with creating lots of heat. All right, so that's all we've got for today's video lecture. Thank you for watching, and I hope to see you again.